Chapter 23 starts Unit 6, and this is really continuation of the confidence intervals and the hypothesis test that we were doing in Unit 5 with some minor differences. So in Unit 5, we were working with categorical data. We would start with a sample, and the sample would ask a question like, do you have health insurance, yes or no? From there, we can make a confidence interval to estimate the proportion of our population that has health insurance. We could use our sample to answer a yes or no question from a hypothesis test. For example, is the proportion of people with health insurance greater than 65%? Now, in this unit, we're switching over to quantitative questions. So instead of asking, do you have health insurance, yes or no, we're going to be asking something like, how much do you spend on health insurance? That's going to change the standard deviation for our problems. And it's also going to change the wording because we're no longer talking about proportions, and instead we're talking about means and averages. Now, we've actually done some quantitative data problems before in Chapter 18. That's when we were first introduced to the central limit theorem. The central limit theorem just said that it doesn't matter what the shape of the population distribution is, okay? Even if it's skewed, as long as we take a large enough sample, our sampling distribution is going to be approximately normal, okay? The number we're looking to meet is 30 or more for our sample size. And if we have a sample of that size, we don't care about what the population looks like. Our sampling distribution is going to be centered around the mean mu, and it's going to have the standard deviation sigma over radical n. Now, the issue is that we pretty much never know what sigma is. Okay, for us to really figure out, for example, the standard deviation of healthcare costs for all Americans, we would have to go out, we'd have to ask every American how much do you spend on healthcare, and we'd have to find out how much those values vary around the mean. And if we talk to every single person to find out what this true standard deviation is, we probably also have found out what the true mean is, which means there's no need to estimate it with a confidence interval. Okay, we would know it because we've already performed a census and talked to everyone. All right, there'd be no need to do any hypothesis tests because, again, the hypothesis tests are about a population, and we just performed a census to figure out what this is. So instead, we don't know what sigma is. We just take a sample, we get an average from that sample, and along with that average, so the average is x bar, we get a standard deviation s, and that's what we're going to use in place of sigma. Now the problem is estimating sigma, the standard deviation of the population, with the standard deviation of a sample introduces additional variation into our distribution. Now for that reason, and let me reiterate it because it's important, it's when we don't know the standard deviation of the population and we're estimating with the standard deviation of a sample. Okay, for that reason, we can't use the normal model, and instead we're going to be using something called a t model or a t distribution. There's many different t models. Okay, there's actually one for every different sample size, and it varies on something called degrees of freedom. This is just the sample size minus 1. Up here you can see the dotted line is the normal model. That solid blue line is a t distribution with 2 degrees of freedom. Okay, they're both unimodal, they're both symmetric. The t distribution has some additional variation in the tails, which is why we can't use the normal model anymore. Now the good news is, other than identifying a problem as a t-distribution problem, they're really similar. Assumptions and conditions, randomization, 10%. You may remember back from Chapter 18, we can't check success-fail because we no longer have a proportion, so instead we check the nearly normal condition. We want to see either a sample size that's greater than 30, and we would say that the central limit theorem applies, the sampling distribution will be approximately normal. Okay, if we don't have a sample size that's greater than 30, we want to check the sample and see, is it approximately normal? We can do that by either making a histogram or a normal probability plot, and we have to draw this out in any answers that are FRQ questions. Now let's talk a little bit more about this t-distribution and how we use our calculator to find these important t-values and p-values when we're using a t-distribution. In part A, we want the critical value of t for a 95% confidence interval with 1 degree of freedom. Degrees of freedom are just 1 less than the sample size, so this is telling us that the sample size equals 2. If this was a z-score problem, we would just add in the left tail of this distribution, go into inverse normal, put put in 0.975 for area, and that would give us a z-score of 1.96 for a 95% confidence interval. Now, if we look down a few options where we see inverse normal, you'll see an option called inverse t. And then again, just like inverse normal asks you for the area, we're putting in that same 97.5%. And it's also going to ask you what's the degrees of freedom for the problem. Okay, that gives us our t-score, 12.706. Part B, same thing, but we have a different sample size, 89, meaning our degrees of freedom is 1 less than that, 88. Okay, we go into inverse t, put 0.975 for the area, 88 degrees of freedom, and we get a critical t-score of 1.987. So these are all for a 95% confidence interval. It's going to change depending on the size of our sample. You can see with small samples, we get something that's a lot different than what we would get for a z-score. But as the sample size gets bigger, right, this is going to get closer and closer to that 1.96. With an infinite sample size, it would be exactly equal to 1.96. But once it gets large enough, it's pretty much indistinguishable. Part C, the p-value for a right-tailed test with a test statistic of t equals 2.09, 4 degrees of freedom. Okay, so the t distribution is centered at 0. We have this test statistic, and we want the right tail there. Normally, we would go into normal CDF. Now we're going to be using the function tCDF. It asks us for a lower boundary. Upper, we're going to put in 99, and it also asks for degrees of freedom. P-value is 0.0524. Okay, lastly, a two-tailed test, test statistic 1.78, 23 degrees of freedom. Okay, it looks like that. Here's just the right tail, so we can do it the same way to start. Okay, we get p equals 0.0444, but remember it's saying that this is a two-tailed test, so whatever we have on this side, we're going to mirror on the other side, which is just going to double the p-value we get from that right tail. So our overall p-value, 0.0888. Now let's apply this to a confidence interval. We're working with one sample, so we have a one sample t-interval. That's the name of this method. And we're going to make a confidence interval for the population mean mu. So we always start with the point estimate. It's whatever our sample shows. So in this case, we take a sample, we find the average for our sample, and that average is x bar. Instead of a critical z-score, we have a critical t-score. And instead of a standard deviation, we have a standard error because our standard deviation is being estimated by a sample. And standard error is given by this equation down here, S over radical n. For example, Trip Hammer Road is a busy street that passes through a residential neighborhood, and the residents are concerned that the vehicles are speeding through their neighborhood at a speed limit over 30 miles per hour. They take a random sample of 23 cars, and this is the data that's provided to us. We want to construct a 90% confidence interval for the mean speed of vehicles driving on Trip Hammer Road. Just like last chapter, since we're doing a confidence interval, this is a panic problem. The p. Instead of saying let p represent, we're no longer talking about a proportion. Now we're talking about the mean. So we say let mu represent the true mean speed of vehicles traveling on Trip Hammer Road. Assumptions and conditions. Randomization. We're going to assume that this sample of 23 cars is representative of all cars. 10%. It's fewer than 10% of all cars on the road. And nearly normal. Remember, we can't do success fail because we don't have a proportion. So we have to make a plot of our data, whether it's a histogram or a normal probability plot. This is a normal probability plot. We're going to talk about how to create this on our graph in our calculator in class. But what we want to see here is a straight line. Okay, and we say something like the normal probability plot of the speeds is reasonably straight with no outliers. Okay, we have to draw this. Okay, we can't just write the sentence without supporting it with a sketch of the graph. Now at this point, we want to find out what does the sample tell us. So we put a list of all those data values in our calculator. We run one variable stats on it, and we find out that these cars averaged 31 miles per hour with a standard deviation of 4.25 miles per hour. Name the method. This is a one sample t interval. We're no longer using a z-score and a normal distribution. Instead, we'd be using a t-score and a t-distribution. And the reason is because we only have the standard deviation of the sample, not the whole population sigma. Write the interval, find the standard error of the sample. Okay, it's a standard error anytime we're estimating it with the standard deviation of a sample. So we get 0.886 for a standard error. Degrees of freedom is 1 less than the sample size. 23 cars in our sample gives us 22 degrees of freedom. Go into inverse t, put in 0.95, which is that middle value plus the left tail for the area. 22 degrees of freedom, and we get our critical t-score, 1.717. Recall for a z distribution, this would be 1.645. Okay, so it's a little larger, reflecting the fact that there's more variability in the tails of this t-distribution. We can find our margin of error. It's just the t-score times the standard error. Margin of error is 1.521. And then just like previously, we add and subtract that from our point estimate, which was the average from our sample. So 31 plus and minus that gives us our interval 29.48 to 32.52. Writing the conclusion, just keep in mind that we're no longer writing about proportions, and instead we're writing about the mean. We are 90% confident that the interval from 29.5 miles per hour to 32.5 miles per hour contains the true mean speed of all vehicles traveling on Trip Emma Road. Now that last sentence is the most important part, and I want to make sure that we have clear as to what we're not supposed to write. So we're not supposed to write something like 90% of all the vehicles riding on Trip Emma Road drive at a speed between 29.5 and 32.5. Confidence intervals are about average speeds, mean speeds, not about individual values. Okay, so we're not saying anything about all cars. We're saying something about the average of all cars. Okay, another thing not to say, we are 90% confident that a randomly selected vehicle will have a speed between those two values. Okay, again, it's about the mean, not individual cars. This next one is something you guys tend to write when you're asked to interpret the confidence level, and you say something like the mean speed of the vehicles is 31 miles per hour or is between 29.5 and 32.5 90% of the time. Okay, that's not true. There's one true mean. Okay, it doesn't vary. There is some average speed that cars traveling on this road drive at. It's the confidence interval that varies based on the sample, but the true mean stays the same. Okay, and lastly, what not to write, 90% of all samples will have mean speeds between 29.5 and 32.5. This is a popular one. Okay, there's nothing special about these numbers. We take a different sample, we get a different average from the sample. Say next time maybe it's 31.1. If we do an interval with 31.1 instead of 31.0, these numbers change. Okay, the interval that we calculate does not set a standard for every other interval. We're just saying we think the mean is in between those two numbers. What we can say, 90% of intervals that are found in this manner would contain the true mean. Make it more personal, say I'm 90% confident that the true mean is between 29.5 and 32.5 miles per hour. And as one added note, 90% confidence means if we were to take multiple samples and create intervals for each, 90% of those intervals would include the true mean of vehicles driving on this road. Now let's follow this up with a hypothesis test. So same data, we want to see, do they exceed the posted speed limit of 30 miles per hour? Parameters the same. Hypotheses. We're no longer talking about proportions, so instead of a p here, we have a mu. Okay? We're saying that we believe it's 30 miles per hour. We're collecting evidence to prove that the alternative is true, the alternative being that these cars are speeding on the road at a speed that's greater than an average of 30 miles per hour. Assumptions and conditions we checked in the previous example. Name the method. This is a one sample t test instead of a one sample t interval. So you can see our standard error popped up that we found in the confidence interval. And to find a test statistic, we're just going to take whatever our sample showed and subtract the value from the null hypothesis. So we're saying that we believe it's 30 miles per hour. We're collecting evidence that it's actually greater than that. So how unlikely is it for us to see cars traveling an average of 31 based on a standard deviation or standard error of 0.886. We get a t-score of 1.129. Now we go into TCDF. We have 0 in the middle. Okay, we have 1.129 as our test statistic. And this is a right-tailed test because it says in the alternative that we're trying to prove that the mean is greater than 30 miles per hour. So greater is right-tailed, less than is left-tailed, not equal to would be two-tailed. We get a p-value of 0.135, okay, and now it's just like it was back in the last unit. We fail to reject because the p-value is too large. There is insufficient evidence to suggest that the mean speed of cars driving on Chipham Road is greater than 30 miles per hour. Make sure you're talking about the mean speed or the average speed.